Hi, I'm Jared Floyd. I'm a technology strategist in the Red Hat office of the CTO, and I'm pleased to join you today to talk about enabling automotive ecosystem growth through open platform standards. So the automotive industry is currently an industry, well, it's always in transition, but there's a very significant transition in how the software systems, the electronic systems within the vehicle are being developed and are being deployed. There's a number of challenges that prevent the current systems from being able to transition to more agile methods where components can be reused more easily in between different models, uh, reused more easily between different model years, have new components deployed into the field, and so forth. And that's because there's a lack of both hardware and software standardization and reusability. That if you look at what the in-vehicle platforms are in cars today, that they look very much like a traditional embedded platform. An embedded platform typically has a high degree of cost sensitivity, that it's chosen to use basically every single cycle that's available, which leaves little for future improvements that are delivered through software. That it's designed typically as a one-time software load, where an image is loaded to that system and then never updated, or only small patches are ever applied. For these reasons, there's not a great deal of standardization about the software, that the hardware varies very much from generation to generation with patches to support customized drivers and so forth. There's limited connectivity to these devices, and they're basically designed to be deployed and then left in the field and replaced with another system in the future. That's been acceptable in the past. I think that we're all used to our car having kind of old, kind of clunky software in it, but that's changing very rapidly due to new entrants in the market. There's also a large number of ECUs, that's computers in every single car, as many as dozens. I've heard that some models have as many as 100 separate computers. This is because of the supply chain model that's taken in automotive system integration, that any individual subsystem comes as a complete hardware-software solution, and that there are often multiple options that are being evaluated for any module, like an airbag module, a braking module, a mapping system, an emergency braking system. All these are going to be delivered as completely independent hardware and software integrated solutions. That means that even the same software may be licensed through multiple different paths, and that many separate microcontrollers are going into the vehicle, each of which may have supply chain disruptions, each of which may have its own individual development challenges. This also means the development experience is completely fragmented across the ecosystem, that each separate system is using potentially different tooling, and then integration happens through, say, open protocols, but it's very limited in what sort of capabilities can be shared between devices. Also, there's a great deal of interest in making more use of open source libraries and open source platforms, but again, that becomes a great challenge because of the lack of support for each of these. Altogether, this means there's a very high cost of initial development as well as maintenance of these systems. There's no way to necessarily deploy large software updates that bring major new functionality. This also means that supporting a system means not just supporting one system, but supporting every, say, vehicle model year as a completely independent software stream, which, with the importance of security updates, becomes incredibly challenging. It means there's a poor developer experience because each of these are different, and the new technologies are hard to deploy. So to change this, we need collaboration at every level of the automotive industry. And Red Hat, as an operating systems and platform company, we have a great deal of interest in driving that standardization with completely open source tools and open source platforms from the bottom up. This is why we've been a participant in the Arm ecosystem for more than a decade. Why we've strongly adopted and pushed standards like the SystemReady standards to drive standard UEFI and ACPI interfaces. And why we think the efforts around SOFI are so critical to success in the automotive ecosystem as well. We need standardization of hardware platforms, not to the point where hardware is no longer differentiated, but there simply doesn't need to be multiple ways of doing the same base capability across multiple different hardware platforms. We need support for drivers upstream so that it's possible to offer long-term support of not just a couple of years, but perhaps 10, 15 or more years for the hardware that's in a vehicle. This then, by having common software platforms, allows consolidation of all those different computers, all those different compute devices across the vehicle into a smaller number of larger, more powerful computers that then can have a little more margin of compute, a little more margin of memory and storage to be able to take on new capabilities in the future. There's no need to continue to look at the hardware and software that's going into vehicle as purely a cost optimization exercise, but rather this is the new location which value is being developed and delivered for differentiation across different vehicles. This consolidation, the standardization will allow more powerful and more modern tool chains, as well as DevOps lifecycles for doing new component development, new software development, and easily testing and deploying that across large fleets of vehicles. And by working in open source, of course, we get all of the benefits of the open source community to drive innovation much more rapidly by collaboration, by having hundreds of developers, thousands of developers across what might be otherwise competitive organizations still contribute to the same base components that allow for a much more rapid rate of innovation. So the challenges that are causing all of these changes to automotive systems are really the driving of value from not just the hardware and the drivetrain of the vehicle, but to the software that's deployed. And a lot of that is about new capabilities in driving autonomy. As we can take more and more of the responsibility of operating the vehicle from the driver, they have greater demands on what capabilities are delivered for infotainment. Not just mapping, but also entertainment features for passenger video streaming, gaming, more advanced driver assistance to enable that. So being able to have fully automated highway driving and eventually city road driving, and having vehicles that are constantly connected via high-speed networking, via 5G networking to the greater internet. Not only does this mean that there's more capabilities that are desired in the vehicle, but security becomes even more important. That system security, recently the German government, for example, proposed requiring 8 years of security updates just for mobile phones, which have a relatively short life cycle. Imagine what the security requirements are going to be for updates to cars, which have a much longer life cycle on the road, and where simply having them be completely disconnected will no longer be possible with the autonomy or connectivity features that are required for system operation. As I just spoke about, there's a consolidation of these dozens of individual microcontrollers that are scattered across the vehicle for different functions to bringing all those functions together as software functions, not just hardware-software solutions that are integrated, so that those components can be reused across different models or model years, so that they can be updated independently of the hardware, and so that the overall software development lifecycle can be accelerated. There's a strong drive to using newer technologies like Linux containers for software packaging to drive both reliability, security, and isolation of individual activities within the vehicle. And all of this, of course, is because there are new automotive manufacturers that are showing that these more rapid life cycles are not just possible, but incredibly desirable to the end consumer. I think we've all had the experience where our car has the same software experience of a 5-year-old phone and never receives updates. That's not going to be acceptable to the vast majority of consumers in the future once they see vehicles that receive software updates, that receive functional updates at the same rate as their home computer or their mobile device. To deliver all this, feel very strongly that open source and open architectures are absolutely required. That what we're doing is taking a transition from these incredibly vertically integrated point solutions that solve an individual problem using a combination of customized hardware and customized software to an open platform that allows for both independent development of hardware capabilities so that hardware can be innovated on its own cycle completely independently of the software innovation. That those software components can be chosen because they're the best solution that's available for the vehicle that's being produced at that point in time, without having to worry that that software component won't be able to run on the hardware that's already been chosen. Similarly, when new hardware becomes available that's more cost effective, that's more powerful, or that has important new features, the existing investment in software factory and software lifecycle will be completely brought forward to that new platform. And in a lot of ways, this is similar to the same transformation that's happened within the telecommunications industry. Over the past 15 years, we've seen a change in telecommunications from network infrastructure being completely customized hardware with customized operating systems and customized software, to monolithic applications that run on standardized hardware, to applications that then run as virtualized components, as with network function virtualization on standardized hardware. Now we're seeing a transition from those virtual infrastructures for telecommunications infrastructure to containerized platforms, where there's even greater agility by using Linux-based containers for encapsulating each capability within the network. This allows for hardware updates completely independent of software updates, and new software functionality to be able to be rolled out to existing hardware. And that's exactly the same place we are in the automotive journey, that we have a roadmap of success here, from transitioning from completely customized hardware with custom RTOSes and custom applications to completely standardized components. We can perhaps even leapfrog that virtualization step and go right to containerized applications that allow capabilities not just at the infotainment layer, but also encapsulating autonomous driving and assistance features, and even core aspects of, say, body controls, such as seat controls, window controls, even charging systems and drivetrain aspects, all orchestrated within that same Linux-based platform. So our overall connected car vision is being able to use these same tools, these same components as part of a Linux-based OS with open source middleware layers that allow easy portability of application components from the vehicle onboard to vehicle offboard, running in edge compute locations or public cloud or automotive data centers, as well as building a complete development ecosystem that runs in the cloud, that allows for individual components to be continuously developed, continuously integrated and tested, and then deployed out to the field with a seamless open source set of tools providing that infrastructure. And this spans across all of the use cases, from autonomous driving or driver assistance features, infotainment, as well as, say, applications that are being provided either by the customer, by the automotive provider, or even a third party, with components that run within the network as well as in the vehicle, and providing a full ecosystem that provides whatever components are desired by either the integration tier 1 or the automotive OEM. Within the vehicle itself, we recognize that there are different levels of safety criticality. So this is still not going to be a one-size-fits-all sort of solution today. That many capabilities are within the vehicle have no impact on safety. That the mapping application, well, it's frustrating if it glitches, or your audio playback application can be frustrating if it's not operating correctly and playing your favorite songs out of the cloud. Has no impact on the safety of the system. On the other hand, there are absolutely critical safety systems, such as, say, the ECU that controls airbag deployment or emergency braking. That's a little more important that those always work. And so within the automotive world, there's an ISO standard, ISO 26262, which defines safety levels for different pieces of functionality based on the impact of failure, the likelihood of failure, and so forth, and assigns these to levels that range up to ASIL D as the most critical. We think that Linux-based platforms and open platforms are going to be serving those use cases up to an ASIL B use case to start. This includes things that have safety involvement but have either less impact on failure or less likely to fail. This might be things like the check engine light that shows up on your dashboard, or the rear view camera, where as long as you know that the rear view camera is, when you shift into, say, a reverse gear, is either working or not working, but not showing you incorrect information about what's behind you, that's not quite as critical from a safety perspective as, say your airbags deploying if you're in an accident. And so we see that there's going to be a standard hardware platform which has different capabilities for different safety levels. That for those most critical safety areas, there will always be a set of, say, lockstep cores that are running a very minimal safety RTOS for core safety applications. A lot of these are provided via an industry association called AutoSAR, for example, with their AutoSAR Classic platform that's implemented across multiple different systems. But for the bulk of functionality that's running on this in-vehicle centralized compute, we see this being done at, say, an ASIL B or lower level of safety criticality. And so that could involve, say, a hypervisor if multiple operating systems are necessary, or this could just be a bootloader that is running a standardized Linux-based OS that includes a container runtime, a lightweight container runtime for running the individual applications. Instead of integrating everything into one core system image, we see that some automotive middleware components, for example, might be provided there, a message bus across the vehicle, and then applications that could range from, say, an AutoSAR adaptive environment to a Google Android environment to a Genevi type component environment, could all run on this base platform. I think there's still a great deal of standardization and definition to be done about what middleware components for automotive and what communications buses will be most standard. But by having an OS platform that supports all of them, that innovation can still be done collaboratively while vehicles are being produced and shipped to customers running this next generation platforms. So this means there's a lot of collaboration opportunities ahead. Here's just 4 of them that are available today. First, platform standardization. Having hardware that supports these future in-vehicle platforms is absolutely critical because the lead time for hardware production is often so much longer, and the substitution process for replacing your hardware is, of course, much less practical in the field than replacing the software. So that's where we see both the existing Arm SystemReady standards as well as the newly launched SOFI initiative as being absolutely critical. That we need hardware that doesn't require, say, board support packages, because a board support package, as opposed to having drivers that are in the upstream kernel, means that a particular hardware vendor is now on the hook for 10, 15 years, perhaps longer of support in conjunction with the underlying OS. In the past, this hasn't been a successful model. What's been successful is adopting standards for component interfaces, adopting standards for functionality like the bootloader, like device enumeration, like establishing a chain of trust from the hardware up to an operating system to application containers. There's no reason to reinvent the wheel here. It doesn't provide competitive advantage to anyone. And so building hardware that is SOFI enabled, is SOFI ready, is going to be critical to delivering this future of automotive platforms. And I think we all look forward to working with hardware and software vendors to make sure that this is a success. That also includes, again, upstream first engineering for drivers, for support for accelerators like GPUs, for interfaces to cameras and other sensors that are standardized, bootloaders, platform control like power management. All of that needs to be developed in upstream Linux. That these should not be customized components that are brought along with each board. There will still be customization. That's going to be ideally in user space components. Again, much of the camera standardization for making use of the camera acceleration on these boards can be done in user space components, but we need to make sure that so that we can establish the safety requirements for the underlying OS, that those are not arbitrary kernel patches that have to be applied to enable a board. So one place that work is happening is in the CentOS community, where an automotive SIG was recently established. Also, work is being done to evolve the ISO 26262 standard to be able to more easily certify Linux and open source components. Right now, we're starting to build the roadmap for that today, but it can be made much easier. And one of those places that work is happening is within the Elisa group, enabling Linux and safety applications within the Linux Foundation, which covers everything from reference cases to development, process, and tracing, to the tools that are necessary to deliver this. To go into these a little bit more detail, so CentOS is an open source and freely used Linux distribution that also represents the upstream of the components that land in Red Hat's commercial offerings. CentOS is a place where we can work with hardware and software vendors to build a completely open and freely used and usable platform for a variety of different use cases, as represented by special interest groups. One of those special interest groups that was just established last month was the Automotive SIG, to be able to collaborate on automotive software in the open source community. So this is everything from vehicle message buses to standardized components, to be able to have a path to integrate upstream projects more readily, and to curate a reference platform that anyone can use to build in-vehicle platform and have that expectation of compatibility against hardware and software components. The next area, as I mentioned, enabling Linux and safety applications. So Elisa has been in operation for a little over 2 years at this point, and brings together experts from both the functional safety world, that's the domain of characterizing both the requirements and the process for delivering systems that, when they fail in a way that is not likely to, or less likely to, cause injury. So to bring those functional safety experts together with open source experts to be able to chart a path to delivering functional safety for open source platforms. This has been a challenge because that standard I just mentioned, ISO 26262, the easiest way to satisfy it is by following a set of requirements around development process, which are ones that specify large design up front, large piles of documentation, mapping that documentation to individual lines of code, to tests, and things that don't directly correspond to the open source development process. And so part of what Elisa is doing is identifying changes to that process, identifying evidence that can be provided for open source to show that it in fact does satisfy the requirements of that process, and to understand and communicate the requirements for areas like automotive systems or medical devices to the open source community. And finally, there's the ISO 26262 working group that is working on the next generation of this ISO standard. All of these international standards are, of course, continually works in progress to represent the state of the art in the hardware and software worlds. So one effort that Red Hat is engaged in, along with the rest of the community, is to establish stronger guidelines and easier paths to certifying open source software and establishing best practices for development of open source software to achieve these functional safety standards, these functional safety certifications. So that's just a quick overview of the work that lies ahead, and the path that we have for delivering much more capable hardware and software systems into in-vehicle platforms. I hope that you'll join us on this journey. Thank you.